Hello, everyone. My name is Rohit Sathye, and my research topic is vulnerabilities in smart contracts and an analysis of the security tools that are often used to check for any security flaws in these smart contracts. So, security is a large part of security is working with tools. We have tools for almost all of the aspects, be it threat modeling, vulnerability assessment, even for ethical hacking. Security revolves around tools, and hence it's rather important to know which tools are the most efficient ones with the possibly lowest system overheads. Going to, sorry, going to the motivation for this project. Smart contracts is rather a recent and upcoming domain. I mean, blockchain was developed just a decade ago, and we see that a lot of the finance often revolves around cryptocurrency. I mean, it's rather booming these days. And an analysis of security testing tools for smart contracts is rather crucial because the core component of blockchain, or rather cryptocurrency, is these smart contracts, because these are responsible for the transfer of funds, storage of funds, and the movement of assets in this distributed network. And what makes this rather much more serious to execute is that the blockchain is immutable. I mean, once any changes are done to the blockchain, those remain there permanently. I mean, of course, there are ways in which these can be reversed, but it's rather a very last resort in case anything happens. So it's extremely important that before anything is sent to the blockchain, it has to be absolutely secure. And this is what interests me because it's rather a critical application of security. So we'll discuss the blockchain models. So we'll focus on four models, which are the system model, the network model, a threat model, and the security model. So jumping into the system model for blockchain. So the main components of a blockchain are the code, which is responsible for transfer of funds, movement of assets, and withdrawing funds, etc., etc. Then there's storage. Then there's balance, which is the cryptocurrency that a particular user has. But a user is often recognized by an address. So since it's an anonymous, decentralized system, the players are known by their addresses, and these addresses are protected by hashing. So code, storage, balance, and address are rather the key components of this distributed infrastructure. Now, if we come to who all are the players in this system, then there are the miners. Miners are the people who validate your transactions. So whenever a particular smart contract is sent to the system, it has to be executed, it has to be checked for correctness, and miners do this. Oracles can be considered as users or not users. Oracles are like people with the access to move stuff from off the blockchain to the blockchain. So they're sort of a management authority for the blockchain. And of course, there are the general users, and the important entity is smart contract, which would be rather focusing on in this research. Smart contracts are responsible for most of the basic functionalities of a blockchain. So this was the system model, and now we'll jump into the network model for blockchain. So the blockchain consists of nodes, and since there's a distributed system, it consists of a huge number of nodes, and it's these nodes that are, we can say, the processing unit for a blockchain network. All the smart contracts are executed on these nodes. So executing, or rather deploying, a smart contract to a blockchain has several steps to it. So the first is certainly compilation. So whenever a new contract has to be pushed on the blockchain network, it has to be compiled first. So the contracts are written in a high-level programming language like Solidity. It can also be written in JavaScript, but Solidity is like the most popular language for writing smart contracts. Once they're successfully compiled, they need to be deployed to the network. So this deployment phase is done in the nodes itself. After they're being deployed, there has to be an initialization to the smart contract. This can be the initial transfer of funds, or the window in which the funds can be transferred. or the individuals to which these funds can be transferred to. So there are a number of parameters that need to be initialized before a smart contract is deployed. And then comes the step of validation, which is rather a very important step, because validation is where a smart contract, or validation is when we decide if a smart contract would be a part of the blockchain or not. And this validation is done by a group of nodes known as the validators. And these are like nodes with a higher level of authority in the network. And once a particular smart contract is okayed by the validators or is given a green flag, then this contract is sent to the network, and every node then validates this transaction. So there's like a two-way correctness to this thing. And once a smart contract is validated, it is then executed on these nodes and then pushed to the network. Now, obviously, execution requires some computational power, and this computational power is denoted by gas. It's what we call gas fees. So to execute any smart contract, you need to pay to the miners who are putting in the efforts to compute the contract, and this is what we call gas fees. And of course, the results of the computation are then stored to the network or stored to the ledger, which we call as the blockchain database. And this blockchain then goes on growing in number as many smart contracts that we execute. And it has to be remembered that this is rather immutable. So once a particular execution is done, it stays on the blockchain forever. Going to the thread model, smart contracts are at a high risk because of the critical functionality that they execute. So code vulnerabilities can be integer overflows, underflows, they can be unchecked return values, they can be use of deprecated type defs, all of which we would be seeing in the next slides. Then there's also the risk of malicious code. Malicious code can be responsible for a denial of service attack, or a malicious code can be responsible for entirely removing contracts off the blockchain or making them useless. Then there's social engineering attacks, which revolve around phishing attacks or pulling data from social media websites and all. Then there's supply chain attacks. So one thing about blockchains is there are like a huge number of dependencies when it comes to executing anything. Even if we want to set up a local copy of the blockchain, we have like large number of dependencies, right from Node to Hard Hat and JavaScript. So in case there is any, I can say, any loophole in one of these dependencies, then that can rather be of risk to the blockchain, because it's rather going to inherit these properties during its functionality. The fifth is governance issues. So there's the DAO, that is the Decentralized Autonomous Organization, that usually looks after blockchain. But if there's any compromise in the governance, like let's say if a large number of nodes are compromised, then that can again render the system as useless, because then malicious code can easily be executed and validated. And this is in fact a type of attack called the 51% attack, wherein 51% of the nodes start misbehaving. Then there's the security model, which consists of like basic steps that we can take to ensure that our smart contract is safe. So the first being implementing robust access control. When there are like so many players in a blockchain, it's rather important to have an access control, because we cannot have everyone having all the access. So the first one is an ownable pattern, wherein the owner of a smart contract becomes sort of the admin of the smart contract and is given the complete access of the smart contract. But then again, this can cause issues with the system being decentralized, because having a singular owner does mean that we have a centralized system, and which sort of goes against the principles of blockchain. So we have a role-based pattern, wherein we have a role-based access control. So we have a group of people who are given particular accesses. So it's not a single person, but it's a group of people, like for example, validators. So this is role-based access. Then using safe code functionality like assert, revert, and require. So these are how can I say, these are like keywords that are specific to Solidity. And these are what make the system secure, because let's say a require statement is something like it's a combination of if else and exception handling. So you need a particular condition for that to happen. And if that's not satisfied, then it throws an exception. So it sort of stops the execution of the code, and which is rather important because we do not want any malicious code or any functionality to be executed. So a require statement is thus used to validate user inputs. An assert is used to detect internal errors, and assert is like quite common. It's used in most of the languages. And a revert can also be used as an if-else statement that triggers an exception if the required condition is not satisfied. So the revert can be used explicitly to prevent reentrancy attacks. So other measures include testing contracts and verifying code correctness, peer reviews. Then we have code reviews. Then we need to implement robust disaster recovery plans in case the network comes under an attack. Then another solution can be continuous event monitoring. So event monitoring is also a good way of predicting, not only predicting, but also checking if the system is behaving correctly. Then reducing code complexity is another solution. And the final solution is defending against common code vulnerabilities, which we would discuss in the next part of the slides. So as a part of this project, I have developed 3 smart contracts which have 7 vulnerabilities. And the programming language that I've used is Solidity, since it's like the most popular language used to develop smart contracts. And the vulnerabilities that I have included in my smart contracts and which we would be testing are the reentrancy vulnerability, arithmetic inconsistencies like integer underflow overflow, unchecked return values, access control. Denial of service is something that that's like a network vulnerability. So I've not explicitly implemented it in my program, but we would rather be discussing a brief overview of how a denial of service works. Then I have bad randomness. Then there's front running or exposed secrets and time-dependent exploits. So going to this, discussing the first vulnerability, we have reentrancy. Reentrancy makes use of repetitive calls from, let's say, a malicious contract into our victim contract. So it involves a function called as the fallback, which is responsible for telling us that, yes, a transaction has successfully been executed. But even a simple, how can I say, even a simple restructuring of the program, or just writing a particular line of code before another line of code, can make the program so much vulnerable that it can drain the entire balance of the contract owner. And the most devastating attack on blockchain was rather the DAO attack, and which was responsible for like a theft of around $30 million or something. So this was like the worst attack in blockchain history, and a huge I can say a huge part of this attack was the exploitation of this vulnerability called reentrancy. And the solution for it was rather unusual, which is called a hard fork, which is actually changing the state of the blockchain. And it sort of went against the principles of immutability. So this is rather not a fancy, or rather not a good solution, but it was necessary. So let's take a look at the reentrancy program. So this is the DVSC contract, which can be a vulnerable smart contract. That's what it stands for. So this is the code that I've written, which contains various vulnerabilities. So if we check on the reentrancy, this particular function, which I have highlighted here, that is the reentrancy attack. I mean, obviously we need another contract which calls onto this contract, but then this lines 21 to 23 is what makes the reentrancy attack so dangerous, because we have initially we need to see if the balance is greater than the amount that is being asked to withdraw. And if we are satisfying that particular condition, then we have this particular function, which is message.sender.call. And this is what calls the message sender for how much amount needs to be withdrawn. And this is a special solidity call, and the return value of this is like a Boolean value. It can be true or it can be false. So in case it's a false, we again put a require statement, so that in case it's a false, I'm thrown an exception that you can't execute this further on. But this statement right here, balance is equal to balance minus amount, this should not be here. This should actually be before we send the call to the sender, because in this case the money is getting deducted, like the money is being sent to the owner even before it's being deducted from the balance. So let's say if I have another smart contract which just calls on to this function, then like for example, let's say I have a balance of $100 and I need to withdraw 10. So in this case, I'm going to ask for $10. And when this particular function is executed, it's going to give me $10. But it deducts the amount from the balance after it sends me the $10, which is rather wrong, because let's say if I make sure that this particular statement gets executed repeatedly, then I can ask for 10, 10, 10, 10, $10, 10 times until all of the balance is drained. And this is what exactly a reentrancy attack is. So the simplest solution for this attack is just changing this to this, and now my balance is deducted. Now it's deducted first from my amount, and then it checks if this particular line is executed or not. So in this case, if I ask for, let's say, $10, it's going to first deduct $10 from my balance. So my balance is now 90, and then it's going to send this money to the person who wants to withdraw. And if he sort of replays this particular line again, then he's not going to get any money, because that money is already being drained from the contract. So this is how we can protect against a simple reentrancy. The next type of attack is arithmetic inconsistencies, which involve buffer overflows, not buffer, sorry, which involve integer underflows and overflows. And they also involve using deprecated enumerations, like a keyword called var. So again, we take a look at the program. So we have like two variants for it. There's the underflow variant, and then there's the overflow variant. So the underflow variant is, what it specifically does is, sorry, this is not the contract. So let's say if we have an amount that is really large in this case, so if my balance minus amount is something that really falls under this variable value difference, then in that case, it might throw me an exception, or it can misbehave in this sense. Or let's say we have the overflow variant, which is from line 36 to line 40. So in this case, let's say I'm depositing a large amount to my balance. So generally I do a balance is equal to balance plus amount. But what if this exceeds the definition of balance? So like in this case, let's say I have a balance as an integer, an 8-bit integer. So in that case, the maximum value that it can have is 255. And let's say if I have a balance of $200 and I want to deposit an additional $100, in that case, this is going to exceed the limit of balance. And that is exactly what we call as an overflow attack, or an overflow variant. This is not exactly an attack, but it's an inconsistency in the contract that can cause it to misbehave. And so a simple solution for it is this require statement here, which just checks if my balance plus amount is greater than my balance or not. So in our case, let's say if the balance plus amount really exceeds 255, then it just starts from 0 again, and now it falls under the balance. So that's how we detect an overflow. So this was about overflow and underflow attacks. Now another type of vulnerability is unchecked return values. So solidity involves low-level calls like call, delegate, call, send, etc. So unlike exception handling, they do not stop the execution of the program. The return value for these are Boolean, which are true or false. So even if my low-level function call fails, it just sends me a false and continues the execution of the contract. So it's important to have a check to see if, in case if it's a false, then we need to just abandon the program. And this is where we are doing it. So if you see line 33, we have a message.sender.call, and we are not exactly catching the output of this particular system call. Like if you see line number 21, I have a Boolean variable called return, which is actually catching the Boolean output of my message.sender.call. And we have a require statement which says that in case if it's false, then it should be a send field and the execution should stop. So on line 33, I do not have such a mechanism in place. And this is what we call as not catching any return values or unchecked return values. It's a rather simple vulnerability to understand than reentrancy. Then there's access control. Access control is like, it might seem very simple, but it's actually number 5 on the OWASP's top 10 vulnerabilities. And the very basic mistake is using the keyword public instead of the keyword external or private. So in the first line of the program, if you see from lines 12 to 14, I have a function in it which says that the sender of the message or the sender of the contract should become the owner of the contract. But as you can see, this is a public function. So there can be a chance that anyone can call to this function and become the owner of the contract. And so instead of public, we should have an external here. Now, denial of service is something that's not exactly because of a smart contract, but it can happen because of a vulnerability in a smart contract. And it's not exactly a part of my program, but we'd rather have a brief overview of how it can work. So I have like 2 variants of a denial of service attack that can happen. In the first case, we have a function called select.nextWinners, in which case the function selects the largest winner based on the computation of I. So it's actually a game wherein upon based on the value of I, the largest winner is declared. So and it's given in the comments that this is a heavy code. So in case this particular heavy code has some loops that just sort of result in a core dump, or they just go on recursively calling each other, in that case our function would just be stuck here and no next winners would be declared. And this is what is a denial of service. Another variant of this is, let's say there's a game which says that it says that to become a president, you have to publicly bribe the previous one. Now, if the previous president is a smart contract and it actually causes reversion on the payment, then the transfer of power will fail and the malicious contract will remain president forever. So let's say we have a require here and I'm transferring the price to the president. It should be greater than the price of the previous president. And I have a president as message sender. Again, I'm not having any checks on the return value here, which is rather another vulnerability. So in case it's a false, so the power is never going to get transferred to the person who bribed the previous president. So now it's again a denial of service because a single contract has the absolute access to everything. Another vulnerability is bad randomness. Bad randomness is like using a predictable value in case of a random one, like for example, using a hash of a block for a random value. It's actually not safe because if the hash is recent, if the block is recent, then the attacker can easily compute the random number. And this I've seen this in my third contract, which is RevSC3. And in here, I have a uint block number. And here I have a block hash block number. And in this case, I'm using a block number like a hash of the previous block. And this is rather very much unsafe, because the entire network knows what the address of the previous block was, and they can easily hash it to obtain the block number which I've used in this case. So this is like using this hash to generate a random number is really vulnerable, because since everyone now knows what the seed is, they can easily compute the random number. So this is another variant of the bad random attack. Oh, I'm gonna push past 30 minutes. Sorry. Then there's front running. Front running is really simple. It just states that if you have some data, some private data really exposed, then it can be really harmful for the program, because then others can see this program, and let's say in an auction they can overbid your price and get the resource. So private data should never be stored in a smart contract. And again, this is in DVSE3, it's just a single line which says that you int my secret sol. So this should actually be private, and so it cannot be accessed by other people, or rather changed by other people. Then there are time-dependent exploits. So smart contracts rely on the current time. And since all of the computation in a smart contract is done by miners, the value of these time functions often come from the miners. So since the transactions miner has a leeway in reporting the time, they can have some sort of vulnerability introduced, which sort of bans for their benefit. So it's rather advised that good smart contracts should never rely on time that is being advertised from miners. And so vulnerability for this can be seen in DVSC2, wherein I have this function called time exploit. So require now greater than this particular value. So what this state now is like the current time, and this is like the value in milliseconds for a system clock. So this states that execute this particular thing in the future. So it basically says that transfer this many ether to me after 10 days. So this is actually wrong, because it should not happen. And this now function should never be trusted because it comes from miners. Oh, I may have skipped an arithmetic exploit here about deprecated data types, which was like the third variant in integer overflow and underflow. So let's say in this case, if we use the var keyword, then var keyword takes the value of the smallest possible integer type def, which is like an 8-bit I. So if I use var I here, so instead of iterating 1000 times, it's just going to iterate 255 times and just go back to 0. So that means that it's going to be stuck in this for loop forever and consume all of the gas. Now, coming to vulnerability scanning, vulnerability scanning has like 4 methods. There's code review, static analysis, dynamic analysis, and penetration testing. So code review is like simple code review, checking for syntactical errors, logical flaws, and other vulnerabilities. And it can be used to mitigate like simple vulnerabilities in the contract. Then we have static analysis. Static analysis doesn't exactly execute the input, but it rather checks for which possible paths a particular smart contract can take. And this is actually the working of the Slither tool. Slither is like a static analysis tool, so it doesn't exactly execute the input. And for research purposes or for using open source tools, these are rather the best to use because they don't exactly cost any money or cost any gas. Then there's dynamic analysis. Dynamic analysis actually involves compiling the contract and feeding it with inputs. So it can identify vulnerabilities that only appear during execution, which is rather not possible for a static analysis tool. But the downside is that it can be more time consuming and it requires more resources. Fuzzing is like a very good example of dynamic analysis, and we have a tool which is actually a fuzzer for smart contracts. So fuzzing is rather the best thing when it comes to dynamic analysis. And then there's penetration testing. So penetration testing is not widely used for smart contracts, but yeah, it's rather a way in which we can use smart contracts. So taking a look at the tools that we're going to use to check our contracts. So we have Echid now, which is a smart contract fuzzer. We have Slither, Mithril, Securify, and Remix. So Slither is completely written in Python 3, and it has like 76 mechanisms for detecting vulnerabilities. Its ability is to can analyze smart contracts written in Solidity versions of greater than zero point 0.4, and it's open source. Most importantly, it is a static analysis framework written in Python 3. Then we have Echidna. Echidna is a Haskell-based program which is actually a fuzzer for smart contracts, and thus it involves dynamically feeding it, it's not dynamically feeding it different kinds of inputs. Now this thing rather needs gas, and so it did require me having some ether with me, so I haven't executed functions on Echidna here, but it does have a functionality of very basic static analysis tools which can identify a couple of grave vulnerabilities. Again, this is open source, but the drawback is that it requires invariants in its program. Then there's another tool called Securify. Securify was developed by an ETH Zurich security lab, and it supports 37 vulnerabilities. And it has the ability to analyze contracts written with Solidity versions greater than 5.8. Then I have Mithril. Mithril is a part of another tool called MythX. MythX is again a dynamic analysis tool, and it's actually not open source, but it's rather the best tool for analyzing smart contracts because of its large number of vulnerability detection functions. So Mithril just makes use of a couple of free-to-use functions of MythX. So this thing rather here is like the output of what a MythX gives us. So as you can see, any sender can withdraw ether from the contract account. That's a that's a reentrancy vulnerability that it addresses. Then the arithmetic operator can overflow, that's underflow. It also identifies randomness of the number, like block hash as a source of randomness. Then it also looks for other time-dependent vulnerabilities. It also checks for bad randomness, sorry. Then there's Remix. Remix is like an IDE, which is used for programming smart contracts and Solidity. It's not exactly a tool for analyzing security vulnerabilities, but it has basic functionalities for checking like reentrancy attacks, but it's basically used for developing smart contracts. Okay, now this is like a consolidated table of what were my observations when I sent these three contracts to the tools. And the test bench that I used was the ETH security toolbox. But this is like a high level overview. We can see that Slither is preferably the best open source tool, which is also used for static analysis for checking vulnerabilities in smart contracts. Remix, on the other hand, doesn't perform well. Echidna is good, but it doesn't perform well for medium and low level vulnerabilities. Slither, on the other hand, works for a large scale of vulnerabilities. So now I'll have a short demonstration of how we can check these vulnerabilities with Slither. So I have used the ETH security toolbox called the Trail of Bits. I tried using this on Ubuntu, or rather cloning the Git repository, but due to its large number of dependencies, it's sort of unfeasible to use it on Ubuntu. And since my laptop just has an 8 GB RAM, it's been rather difficult to execute this concurrently. So I just opted to take this Docker container called the security toolbox. It's from ETH and it's open source. So in here, I have like, I've logged into my Docker container, and as you can see, I've already placed my contracts in a folder called Not So Smart Contracts. And what this does is it's just segregating these based on what vulnerability they have. And so in case my contract doesn't have a particular vulnerability, that folder is empty. Like let's say in this case, if I just go to, sorry, let me just clear this. And if I go to race condition, so I don't have a race condition in my smart contracts, and it's just empty. It doesn't have any contract inside it. But let's say I have a reentrancy in my smart contract. So what I'm going to do is I'm just going to hop onto reentrancy. And now I have a reentrancy.sol. So all of these other programs are like they already came with the container. So those are not exactly mine. But reentrancy.sol is like the code snippet in my dvsc.sol. And so it's really simple to do a Slither analysis. I just type Slither reentrancy.sol. Yeah, and it gives me an exact, not going to say a review of what functionality I may have. So it says that should be declared external, and green says that it's detected the vulnerability, and red says that it's actually a grave vulnerability. Now, if I go to an integer underflow attack, so let me just hop back. Oh, oh no, I just hopped back a lot. So if I go to cd integer overflow, and now I just type slither integer.overflow sol, and it shows me that it has this, but it's detected this particular vulnerability. So I've used the Solidity version 0.4.21. In the higher versions of Solidity, the var keyword is actually not used, so they have actually patched that particular vulnerability. But since I wanted to exactly show how var can be misused, I have used Solidity 0.4.21. Another can be bad randomness. So I'll just hop off to, oh, oops, sorry, bad randomness. I think I'm running out of time. Oh no, oh no, oh no. I think it's just past 30 minutes. So so this is how we can actually execute these functions. So I choose to show my demonstration on Slither because Slither is like a comparatively easier tool to use thanks to the ETH security toolbox, whereas the other tools do require some dependencies, and the time they take is actually longer than what it took me for Slither. So Echidna like took around half an hour for execution, and Slither was easier to execute. So I'd again jump back to my slides. Oh no. Okay. Coming to the challenges and learnings, so the biggest challenge was that there's a large number of tools, but not all of them are open source. And a few vulnerabilities are yet to be exploited, something like a zero-day exploit. So there are no tools that can identify these vulnerabilities. Another challenge is that dynamic analysis requires gas for execution. And since this was not a funded project of any kind, I've just limited myself to a static analysis tools. But the biggest learning of this project so far was obviously programming smart contracts is not really difficult, but provided you have a good grasp of Solidity programming, it can become easy. It can become easy to program a smart contract, but it is difficult to make it secure. And a smart contract should have the highest level of security possible. And since smart contracts are highly critical due to the immutability of blockchains, their execution is irreversible. So it's really important to focus on security when it comes to smart contracts. Yeah, that was all which I had to show about my project. Thank you very much for your time. Yeah, thank you for being with me.